We're back. Wait, nope, now we're back. Gotta get good at speed running, sharing these, so that way there isn't an empty space here at the start, but here we are. Gonna do some more framing design. Soon as the Twitter would like me to, there we go. We do some weld calcs today. Weld calcs. It's gonna be fun. By request, we're going to do something I think is interesting, which is calculating knockdown effect for welds. So it's a common thing that you'll end up welding a frame. Specifically, you see it a lot in steel. Aluminum's tough. Aluminum is it's harder to weld. So first of all, there are fewer processes you can use to weld aluminum. One of them is TIG, which I think stands for tungsten inert gas. Technically, I think you can do MIG, but other processes like I believe stick welding, GMAW, etc., they're not compatible with aluminum, as far as I know. I could be wrong, but I've never seen it. Oftentimes, when you hear people talk about stacking dimes, they're doing it with TIG welding. It's because TIG welding and aluminum are like that meme where they're shaking hands and they just stack puddles. That's what it's for. Um, so the problem with TIG welding is it's really tough, especially on aluminum. So it's kind of like the holy grail of welding. Anyways, all that to say, something interesting happens when you TIG weld aluminum, and that is it turns into well, essentially becomes useless. Not useless, but it anneals the aluminum. So you get what's called a heat affected zone around the weld area. And that's bad because your 38 KSI yield strength um, on aluminum goes to like 9 or 15 KSI. So you actually more than half your available strength. And so believe it or not, what we're looking at here, these two tubes being joined, it could be that this is actually stronger than if you had welded it, interestingly. And so we're going to figure out what the weld strength is going to be, and then we're going to figure out what the pull and push strength of this joint is going to be. Before we do that, we're going to do a little CAD, but I am going to say that we're going to add these calcs in to do today. And we did actually finish this yesterday, so um, so we'll calculate weld stress today. No, weld strength. Okay. And then we'll compare the two actually. And I'm going to look stupid today because I have not calculated I haven't done a weld calc in a while, so it's gonna be fun. So that's for today. Um, Actually, before we get into that though, I actually want to quickly model this because the gents at FabWorks actually sent over the corrected model. So they are going to keep me out of my misery trying to model that from scratch again from a screenshot in a video. So that's nice. So we'll do that first and then we'll get into the strength checks. And we'll rework these calcs to reflect those strength checks. If you're curious, you can find these checks on the GitHub. And I will actually post that now so you can follow along. So if you want, go ahead to the GitHub. Under analysis here, you will find the calculations that we're currently working through. Looks like that got truncated. I have to save that. Do this again. See if that sticks. There you go. Okay. Yeah, those calcs are on the GitHub. Go take a look at them. You'll need Python and Jupyter to do that. I'd actually do a video where I show just like a 20-minute video on how to actually work on open source hardware on GitHub and just say, okay, this is how you export CAD files, this is how you import CAD files, this is how you manage part numbers, this is how you put your analysis on a GitHub repo, these are the tools you need to do it, here's how you install Python, all of that fun stuff. I might actually do that at some point. But for now, I'm going to just keep working. Okay, so let's look at actually before we get into calcs, like I said, let's actually model this out. So we had this version of the frame, which was kind of a bummer because you have these overhangs. Kind of a bummer. It was a bummer. So what I'd like to do is find essentially a version of this frame where instead of having these overhangs, it looks something like this. Where these frames are actually capped out somehow. And I think we're able to do that now with the new design. So we're going to do a 1 meter by 1 meter by 1 meter tube frame using this design. All right, boys at FabWorks, I'm sorry, but I'm going to have to get rid of your beautiful logo here, which is beautiful, by the way. I do love this logo. But we're going to, like I said, we're going to pull this frame back a bit, so it's going to go away. But we still love and respect you and are very thankful that you made this framing system open source. So you're contributing to the art, and we appreciate that. So we're going to give ourselves about ½ inch for that stress to develop around the joint here. When actually this is not really going to see any stress. This is going to see the load bearing capacity develop. So we might actually bring that back a bit. I want to find actually we'll leave it like this because what we'll do is to actually round this out to that 1 meter. We'll use this edge to do that. Let's actually animate this real quick to show exactly what is going on here in terms of what the frame actually does to lock into place. I should have had this video cooking. Just give me a second, I'll find it. Pull that video up real quick. So there's an actual video showing how this system comes together. And I should have been playing that to make this make more sense. So it's gonna make noise for a second. Bear with me. Okay. Here's the video. Nope, wrong video. More awesome tube cutting though. You love to see. Tube cutting is the future. Yes, this is what's going to do. If you don't believe me that tube cutting is the future, let me show you the sample from 10 years ago, back when this was incredibly expensive to do, but is now more affordable. Where are So shout out to Bassett Inc. Um, oh, can you not see me? My video's not up. Huh. Keeps doing that. How do I bring this to the front? I'm gonna do this live. Should have checked that before I got cooking. That's too big. That's just right. Okay. All right, so here's the sample. I actually got this made more than 10 years ago, but I mean, this is thick gauge too. It's like 1/8 inch gauge. It's pretty cool. So shout out to Bassett Inc., based out of Pennsylvania. I used to work there. I used to make stages for Lady Gaga there. Okay. So cut tube is cool. Why is it cool? Because you get closed sections, and closed sections are good and strong and stiff and strong. Did I say strong? But the cool thing too is you can essentially if you have one of these laser cutters and this tube cutting service, you actually really don't need 80/20 anymore. Like if 80/20 was this is not investment advice, yada yada yada, but if 80/20 was like a publicly held company, I would actually treat their stock as directly related to the national capacity for cutting tube laser like this because it gets rid of the need for on-demand sort of modular framing that you can snap together because you can just model it in CAD however you'd like they did, and then just cut it to your heart's content, which is great. Um, so yeah, there are a couple limitations. Um, by the way, specifically on aluminum. Aluminum tends to come as extrusion in these hard corners, and so you get stress concentrations at the edges here. F over A equals stress, and so your A goes way down. And you get a notch factor, not a notch factor, but there are these stress risers caused by this. So hard corners you always want to avoid. Now with steel, you get a little bit more of a relief because it tends to be hot rolled and welded. And that's, if you don't believe me, go look at a piece of steel tube. And if you look hard enough, you'll probably find the weld line. For aluminum extrusion, there isn't a weld line. And look, I was right. So right there, there's the weld line. And this is steel. So what they do is they actually roll this, they actually have just a sheet of steel. They heat it up, then they form it and join it at the seam, and then they actually line weld this. And the reason why you don't see it on the outside is because they grind it away in post-processing. But you can still see it on the inside. So I challenge you, as you walk around the shop, go and try to find a piece of aluminum tubing that has a weld line, and you probably won't. Getting back to the topic though, because they form it, you get nice radii. And these radii act to reduce stress concentrations at the outermost fiber of your tubing, which is actually where you want hard corners the least in some cases, specifically in bending. Um, so that's the downside of aluminum tubing is, or some aluminum tubing. So they actually have aluminum tubing that does have that round corner, and I don't know if it's more expensive, but it's just something to be aware whenever you're just choosing your tubing. Is if you get the hard corner variant, it is dimensionally easier to work with. It being totally flat across the surface is really nice, but you do get the downside of the stress concentrations. So keep that in mind. Okay, enough philosophizing on tubes, and let's get to modeling. So I think the way I did this last time was a little nasty. I think what I want to do is actually build out some construction geometry and then try that way. I don't actually know if this is the right way to do it, but I'm going to just put out my planes where I want them. So that's 1,000, so that's 1 meter. Do another one at another meter, and then we'll do another one at another meter. And actually, I keep forgetting to do this. I'm going to put keyboard presses on so you can see what I'm doing. And it didn't work. How about clicky clicks? Nope. I'll do that next time. Actually, maybe I just have to relaunch this project. Nope. Okay. You'll see that next time. Anyways, I've got my 3 planes, which does define my frame. So I'm going to scale these out so you can kind of see what I'm doing here. So now if I look at these, kind of see where the limits of this frame are. So we'll actually use those as ground truth for modeling all of this stuff. So right off the bat, I want to move this to be in line with the coordinate system, so that way we have the base sort of set for where we're going to work from. So I want this dimension. They're going to add copying dimensions here soon. I have that from a little source that I will be telling you about soon. So this should be flush now. Okay, that's flush. And so now I can start using some of my favorite direct modeling tools like replace phase. Oh, actually, now that I'm thinking about it, this is giving me some ease of modeling. So I can actually just mid-plane this. Yeah, that's going to make this real easy. So I'm working essentially in a quadrant. And where did my other plane go? Did I get rid of it? I guess I doubled it. This goes out 1,000. Actually, I want to go the other way. Yeah. I'm going to work in the coordinate system correctly. And is this on center? Let's see. Is this on line with this? It is. Great. Okay, so I'm just going to rotate this. Okay. So that is not, this is also going to need to move, which is 25.4. So now this is flush. Okay, so this is kind of like the boundary of what the frame can live within. And I'll draw it out real quick. So 1,000, 1,000. And the reason for this is because we want to create a 1,000 by 1,000 frame. That's why. And yeah, that's really why. So this is just a modeling hack, essentially. It's not for any engineering reason. Yeah. I'll hide this sketch real quick. So let's get this back in the right place. Our the snapping to the world coordinate system is bumming me out. All right, so that should be 500 away from this plane. And it is. Great. Now I replace face. And now we think about, do we mirror this or do we rotate this? I think we rotate it. I think we rotate it. But we'll find out. Actually, first we want to make this, we want to carry through the features of this part. So you can do it on both sides. Actually, you want to do that for all sides. And we're going to do that by, I wonder if you can actually just copy face or pattern face. Let's see. Yeah, I can't sing the praises of one of the things Shaper 3D did that I don't know if other CAD packages do. I don't think they do. Is that they allow you to copy faces, not features, not bodies, but faces into a part, which has been super, super, super fast. So this is actually way faster now because I've been able to do this. Okay, so I've rotated this. And so actually for the general rule for the rest of this model, I'm actually going to try and avoid mirroring because it's bad practice in a lot of engineering cases at the assembly level. You can mirror part level. You should not mirror at the assembly level. Don't at me. I don't want to hear about it. Don't tell me why it works in your case. It might once in a while, but it doesn't a lot of the time. And you will find out when you order your parts and you wonder, why don't any of these parts fit? Well, no, wait, why do only one set of these parts fit? It's because you mirrored them. It's such a big problem that I actually worked at a company where they actually had a script that would detect when you mirrored a part and would put it in the part name. So it told the engineer, hey, dummy, you mirrored this part. You mirrored the part. And actually, I think SolidWorks has this built in. Um, so don't mirror your assemblies. Mirror your parts. Inside. Mirror your features within the part. Anyways, end of rant. Let's rotate this. Did I just kill my sketch that defined what I was trying to do? What did I do? No. Okay, so let's rotate this over. Actually, you know what? I'm going to be a good little engineer today. I'm going to name these planes. This is Y mid, because this is actually going to be useful to me later. This is going to be Z end. This is going to be Y end. And what are you? You are... What are you? You seem to be useless. I think I used you to split something earlier. Yeah. I lost my X end, so I need to add that back. This will be X end. It's like a cool AIM scream name. If you're old enough to remember what AIM is. Okay, so now we're going to rotate this assembly over. After I first extend this tube out um, to get symmetry, create a midplane, and then replace face. If you aren't abusing replace face, you are not full tilt engineering yet. Okay, let's rotate this over and see what happens. Okay, we'll join these. All right, so what happens? We have the first leg of our frame. Actually, I'm going to create, now I'm going to leave these out actually. So I'm going to want to reference them later. Put this somewhere better. There we go. I need to stop saying I'm going to put a quarter in a jar every time I say So how does this work? So we have this is now slotted in. We pull it up, the thickness of this tab. which is roughly 7.2 millimeters. Let's call it 8. So this comes up 8. And so now you should be able to pull it out. Like so. That does appear to work. So what happens on this side? Aha, that locks it into the other side. So rotating it is not the move. Yeah, that locks it in further. You actually want what do you want? So we moved it up before. You want to move it down on this side. So rotating is not the move. You actually want to mirror this, which is funny after complaining about mirroring. But okay. And I think we're supposed to mirror this as well. Okay. And we're not going to boolean that. Doesn't make sense. Boolean this. Okay. So now you move this tube up and it disengages on both sides. Yep. So that's good. And so now we want to continue with the theme of mirroring, I think. Join these tubes. And so now we should be able to rotate this up 60, I'm sorry, 90 degrees. Find center here. Rotate this up 90 degrees. Yep. And so that should be in place. Yep. And you move that to the right. Yep. And we should be able to copy this over. First, we want to copy this one over too. So let's actually think about this side of the frame. What happens? Wait, is this right? Oh yeah, it is right. Huh. Anyways. Said okay, so let's rotate this over and we should um we should find center on this one. So we actually did the sketch here, which is useful, but we also want to do it on the YZ plane. So again, we draw a rectangle. Actually, this is gonna have to move up. Damn. Can I just move everything up? Look at that. Can I move this up though? Hmm. How do we fix that? I think we move this up 25.4. See if that works. Ta-da. Okay. So now on the YZ we can draw. Um, where's my, is that right? Okay. So why is this breaking my brain? What happened? So this is, oh, okay, there we go. No, that isn't it either. Sorry, this is hard to follow, but I'm just trying to find the orientation that I'm seeing in my mind's eye, making sure it matches the CAD model. Yeah, okay. All right, ignore the last 20 seconds. So we now we can draw our sketch. This matters because we want to have center point for rotating our assembly around. We're going to do 180. Let's see if this works. We also want to do, I'm going to rename these. Don't want that to be left. This one be left, and this one be top. So these two want to come up too. I should have included those. So edit the target bodies for that. Okay, let's see what happens. So so you pull this tube down to lock it in. And it's the same for this side. So it's looking better. So what is the distance? I think we found our distance that we actually care about right here. So this is the distance we should control. How do we do that intelligently? We just got to brute force it. So I'm going to find this distance and then make that round. So we want 0.955 to get rid of. So we're going to just move it. We're going to brute force it. Actually, I'm getting ahead of myself. We'll do that later. So now we're going to copy this side of the frame over there. So we need to find this distance. Actually, we can brute force this. So I'm going to move all of these over 0.955. So this should be 15 clean. Yes. And we want to do the same to the other side. Again, I'm brute forcing this, but it's fine. Great thing about direct modeling is that it lets you brute force stuff. So now we want to carry this over. We're going to copy it over some distance. and we're going to measure what this distance has to be, and we want that to be, well, we know it's 15, but we have to figure out what it's going to be. So it's 34.2, we want that at 15, so all we'll do is we'll move that over. Dimension, can't believe I already forgot it. 34.2. So 34.2 minus 15. That should be 15. It is. Okay. So here's our 1 meter by 1 meter frame. How exciting. And so now we check the assembly. So this one, these two should be the same, and they have to pull them down. Yep. Yeah. Same for these. It's crazy. I don't actually know how this is going to work. Like, you really just have to build and test this. Yep. Yep. Okay. So there's our frame. And we should add effort holes so that you can replace 4020 with it. I'm sorry, 8020. 4020. 4020 is the, it's what you get at 4020 is the 8020 they tell you that you have at home when you don't. And so what should it have? So in general, let's look at what we're kind of competing with here. So Unistrut is an example of something we want to replace. So Unistrut has these sort of standard widgets. And it's the steel version of 8020 essentially. Stretch channel is what it's called. And so it has holes and slots. So we'll side with, do we want holes or slots, or both? I actually don't know. Slots are good because it gives you adjustability, but holes are good because they're simpler. We do want accuracy. All right, we're going to do just holes to start. So we find a reason we need slots. Before I do, I'm actually going to save. No, I'm going to keep working. So do we want metric or freedom units? We'll go with metric for now. So we're going to have, first of all, we're going to figure out what this distance is. This is the length. This is half the length, and that's 449.2. So let's make this an even number so it's easier to work with. So we'll make that 400. So what we'll do is we'll create, yeah, a new line. We'll make it 400. And we will align it with the center here. Now we can, on a pattern, create we can actually create our mounting pattern. So we're going to use, what's the standard screw size? Let's see how M8 goes. M8 is pretty good. M8 is a standard screw. Could be bigger, but maybe we do 2 holes. I wonder why Unistrut didn't do 2 holes. Because I think 80/20 did. I mean, it's slots, but they give you the ability to mount hardware on two sides. No, they're center focus as well. I know they have double stack like this, but I guess we need a bigger screw. But like, what's a standard? Here's M12. Um, anyways, so we want it on a standard length. So we have 400 millimeters. We have an M12. So that means if we want, what's a an easily divisible sort of number here? So it'd be 400 total length, and let's say you want 10. They'd be on a 40 millimeter spacing. That tracks with me. Why not 50 though? 50 is clean. How about we'll have 8 holes at a 50 millimeter spacing. And let's actually do some sleuthing here and find out what would happen to the other side. Is there any magic we can do? I don't think we can because this is 50.8. So let's see. If we draw a circle here, no, yeah, we'll still be fine. So when we rotate this over, this should intersect with that. Maybe. We'll see. We will see. I'm actually not sure. Okay, so we're gonna have this on a 50 millimeter spacing. So we'll actually pattern that now. We'll do, I think it was 8, and we're gonna do that on a 50. And that should go, why did it leave the sketch? So 8 isn't enough. 1, 2, 3, 4, 5, 6, 7, 8. It's not giving me the 8 for some reason. Let me see what's going on with that. There it is. Oh, it includes the original, that's why. So we're gonna have 9 total. Okay. Great. Now there's a problem. I don't think that this is going to be, no, it will be. This should be 25 from there. So this might actually work. It should be 25. It's not. Why are you not 25? $24.6. What happened? Oh, I forgot to account for took the center here. I forgot to clean up and make sure that this was at the right offset. So we want to pull this back. It was 24.6. We want 25. So 24.6. How do we fix this? We need to move it down 0.4. Long story short. So this be that should get us to 25. Yep. Okay. So then that's going to be an even spacing all across. So what we'll do is we will extrude all of these and create the mounting profile. I mean the mounting features. And we're going to do this all around. I'm going to do this as a boolean that I can start to manipulate. Let's just double check and see if all this plays out well. So if I undo this, this should all propagate. Yeah. Yep. Okay. Just double checking my work here before I start getting too deep into this. So we're going to boolean from this tube. Actually, no, we're going to mirror these, or rotate them, I should say. Why did that not work? Okay, so now should be able to pull that over. So I'm going to copy these over. Okay. And as a sanity check, I'm going to draw that circle and ensure that indeed these are at center, and they are. Great. So now I can create this feature. So that doesn't look right. What happened there? Why? So this is not 25. This is. So you can see the distance here is off. It's because I messed something up. Let's see what happens. What did I mess up to cause this? So the pattern works on, which side does it work on? Let's just boolean these and we'll see. Okay, let's see what happens. So it works on this side, this side, this side, this side. It doesn't work on this side. What did I do incorrectly here? What is the center distance? 19.8, so some random number that doesn't make sense. It's because the tube length is different. So that's center is 20, it's 75. So it should be 75 and it won't be on this side. It should be 75, but it's going to be probably more. $90. So why is that off? All right, so the common thread here is this copy happens at this center point. Clearly that center point is incorrect. So maybe we need to draw it and figure it out, which is fine. We can do that. See if that center point actually matches. It does. That center point is where it needs to be for the rotation. I don't see why it's bugging. So that's 75. Are my midplanes off? That's telling me my midplanes are off. So what's the, so this is, should be 1,000 away. Yeah. And then this one is, that's also right. So what's going on? I'm totally confused. What happens if we rotate the body over? That's right. Oh, but this one's longer. The other midplane was broken. No, wait, this midplane is also correct, I think. So what's going on? Hmm. Okay, I think I've got it figured out. It's because this offset distance is screwing something up. So I need to find a common center distance between these two sides, or with these two sides in the general frame that's going to work. So what would that be? So there's our problem. We have this center, and it goes through this, but it doesn't go through this. So we have to move these holes in. And I think that's okay. I do think that's okay. So let me just get that distance. 87338. Okay. So we're going to brute force this, and it's a case of do as I say, not as I do, but I think we get there. Okay, so this should be 25 now. If this is 25, then we can keep going. We're good. It's not. But why? I just had this great reasoning for why that would work, and it didn't work. Okay, so why didn't this work? I think it's because it's this distance we care about. Oh, because the offset from this is different. All right. We're gonna brute force this even even more brutally. Do I need this sketch? So we're just gonna find what this should be and then correct that. That's that. So that should be 50. Right now it's 9.9045. I'm sorry, it should be 25. So we're gonna move it that much. So we're gonna go back here to this move. Where was it? This move. I think we might have just deleted it so we can just select these. So we want these features. And they're going to move this copied amount. And this should be 25. God willing. 25. Okay. Now, yeah, if you are wondering if you want to do engineering and you thought the last 10 minutes was boring, don't become an engineer. That's my advice for you. Because it is often tracking down why something's not working and it's a small detail. Not often, it happens. You have to be patient. Okay, so this whole distance is giving me a little worry. This one's fine, but this one is not. So we're going to delete these. Because you can't actually get hardware in there. It's going to collide with that tube. So we're just going to delete those. I forgot to do the other. Well, no, I don't need to do the other side, so that's fine. Okay, so here we have our frame with the details for actually mounting hardware or our little widgets. And that's that. Do they sell something like this? I think it's called, there's mod truss. Familiar with mod truss? Bosch, Rexroth, EcoShape. Maker Beam. What's Maker Beam? So I've seen this stuff, but ChatGPT didn't understand what I was saying. Maker Beam. Maker Beam. I mean, Maker Beam is just a copy of 8020, so I don't know what that is. Yeah, whole series extrusions. I knew I saw this somewhere. I think this is it. No. Oh, whole series. Kanya. I don't know what Kanya is. Base. We've got 50. Or let's just look for a whole. Let's put on whole. Tool clamp. What's tool clamp? Nope. No, no, no. So I don't think this exists. I know I've seen steel do this. I know we didn't invent this. All right. Anyways, so So here it is. So the idea is you can mount things to this. This actually wouldn't work as is because these tab and slot details are probably not moment capacitive. Actually, they might be. It's hard to say. We should just start the analysis and see what it says. But before we get into doing the weld calcs, I want to clean all this up and make it make sense. So we might actually delete a lot of this. And what we'll do is we'll just start from scratch over here and talk about what we're really looking for. So we've got these great calcs, which we're going to save. File these under tinyframe. And all this was ptumblr. All right. So let's talk about what we're trying to do here. What we're trying to do is find out what I do. What we're trying to do is find out what we need is deflection. Okay, well, actually, let me take a step back. We want to be able to select any type of frame dimension. So it doesn't matter if this or if it's this, big or small. We want to know, even if it's, say, this, the same size but way thicker. Different dimensions. There might be reasons for that. You might say, well, you know, I need you know, I need, I've only got 2 by 2 in stock or 1.5 by 1.5, whatever. And we want to be able to support multiple types. And so we should have calcs that tell you, okay, when you switch the dimensions on this stuff, so it doesn't matter if you're doing this one or this one, your design changes, and we need to know what are the things that do change based on this. So right off the bat, these dimensions are all going to be functions of the length of a side. So for input, we're going to have, we'll have output too, obviously. For input, we're going to have, let's say we're only going to do square. So we're going to say, what is the length for a side? Another thing you'll have is the thickness. So what is this thickness versus this thickness, etc. So we'll need thickness. What else changes? Oh, well, what if I do steel? Okay, material. So right now we have 3 variables we can change. think that's it. And so what we need on the output is, what is the length of the tab? Tab length. Oh, another input, force. We know it stays the same, but we need that force. Actually, we'll have fixed inputs. So fixed is going to be force. We never want to exceed, say, 10 pounds. So we have inputs, we have fixed variables, or fixed constants, and we have outputs. The outputs inform the design. So tab length is the only one I can think of right now. Yeah. I guess another fixed dimension will be, no, tab length. I guess general geometry will matter too. Uh, tab, we'll call it tab geometry. Okay. Really, I think this is it. I think you only have tab geometry. So what does this look like? In other words, what is the software that we're writing really, or not software, but the calculations we do, what does it really have to do? It has to take our fixed inputs, which we just outlined above. It then has to do some math. And then also reference fixed values. And then it spits out outputs, which we then, and I'll put a line here to delineate we're jumping out of the system into CAD, which then goes to angry machinists that tell you that you can't make it. So we're only going to focus on this though. And I will convince the team at FabWorks that they can't make it. They've actually already proven it to us. So, okay, so we're going to talk about this now, this input. And we know now the goals. We want the tab geometry. We have to input variables, which are the length, thickness, and the material. Okay. Why are you collapsing? I don't want you to collapse. It's too small. Okay. All right, so what have we done so far? Oh, another output. Factors of safety. FOS on yield for weld and snap. This is a soft requirement because we're just doing this just for the show of understanding how much stronger or weaker it is than a weld. But okay. So let's do that. So first we'll go through what we did earlier. We have the equation that describes deflection as a function of loading for locking tab. And so this is deflection as a function of load, some other things, and just harking back to what I was talking about earlier. That's actually a copy of this. That's where we got this from. And this is the flexure. So this bends down these flexures here. So that will be a driving constraint, and we want to hold on to this equation because I think, actually, do we want this equation? We're trying to maintain input load. So we have P, oh, we want L, so we solve for L, that's right. And we get L somewhere down here. I think all this work here was just a precursor to validate that that their system, that our numbers were actually making sense. And then we solve for L down here. So we actually want to actually get rid of this entire section, I think. We want to maintain actually the second moment of area potentially. Yeah, so we'll want to save the second moment of area stuff. So we'll just start our deleting. Find the prototype deflection. I think we get rid of this. Unless we reference it in the calculations below, in which case we'll save it. Yeah, we do want to save this. So before solving the required locking tab length, we need to find the prototype deflection. Nope. Let's change this. The required locking tab length, we need to find the we solve the deflection equation for L, length of the flex tabs. Sorry, we said locking tabs. I deleted something I actually needed. Check back here. Yeah, that's fine. I'll just get this real quick. Okay. We normalize to the number of tabs in the system for and end up with, yep. Okay. So that's our deflection equation. We're going to use to calculate the required length of the locking tabs. So we declare our L, and then we actually get rid of L prototyped here because we don't. We want to find L, and we don't want it. We want to find L essentially. Then we solve for L down here. I just got a wonderful message from Pete Oxenham. We bust ass at the machine shop while the frickin' engineers sit in the offices and whine. And he said many such cases. Yeah, but let's be honest, Pete. Y'all do your share of whining as well, given the opportunity. That's coming from a professional whiner, by the way. So, okay, so we declare everything here, and then we go further into the definitions down below. So this is going to make more sense. So given that the analysis matches CAD, we actually don't care about that. We can utilize the required deflection as a function of the tab depth. I think this is just complicating stuff. We need to calculate the length of the flexure locking tabs required. Solve the equations of the above equation for I. No, that's not wrong. Solve it for L. P represents the global press force, but we assume, did I copy that? How did we get 12? Oh, that's right, yeah. Because we normalized to the fact that we have 4 tabs, so you divide the load by 4. Yeah, and so here's our equation. Okay, so now we get to solve for L here. And so what happens if we run this? Ueg.newton. Ueg is not defined, it's because I need to run all these cells. Import numpy, done, units, markdown, yep, yep. And so now we should actually spit out, yep, okay, so this is not making sense. So we now have this part done. Well, almost done. So the tab geometry is actually more than that. It's length, it's B and H. Yeah, and it's B and H. So we need to find, we actually need to define B and H as well. B and H being the dimensions of the locking tab. Let's do that. So how do we define B and H? We'll really grossly approximate this. We're going to say, hey, look, this is the length of the tab, and here's what those dimensions are based on that length. I think that's going to be really simple. We'll just do that as ratios right now, and we can just adjust those factors later. So let's go back up here, and we'll set up some inputs. We'll add a cell actually above for this. How do I add a cell? Create new view. What's a view? I want to sell. Let me sell. Where? I want a new cell. I swear to God, give me a cell. I think the keybind is like A, B. Wait, did I just delete it? Okay, restart kernel and run all cells. Yes, that's what I want. I just want to make sure I didn't delete anything I didn't need to. Okay. All right. Give me a cell. How? Why am I having to argue? Oh, there it is. It's that plus sign. Are we having fun yet? Okay, so I'm gonna add an input here. We have um, um, tube width, and that's going to be the same for all sides. So width is equal to, call it tube width, 50.8. Right? Yeah. And so then the tab width right now is this distance from here to here, and that will be essentially B. Right now that is 3.19. Actually, taking a step back, we're going to calculate B ratio, which is like I said, we're going to back this out so that these tab dimensions change as you would change your tube size. And so we're going to start calculating these ratios. That distance right there for this tube size is 3.19, which means that the B ratio value is going to be 3.19 divided by whatever this tube width is. And now we'll do, H doesn't change, that's the thickness. Right? Yeah, so we'll actually have thickness. So that'll be, I think we said H. And we said it's 1.651 right now. So we're going to get rid of these now. This is B ratio. We still need to calculate B. Wait. Yeah. And because we're at 50.8, B turns out to be that's going to be B ratio times T width. And that should cancel out because right now we have the same tube size. So just to check it out, if we print B, we should get 3.19. We do. Okay. So I'm going to move this out of declarations though. Okay. What else do we have to declare? I think that's it. Okay. So now we can solve for L. And so it's saying we need 63 millimeters of length. I don't know if we actually had 63 already. But let's just look through the equation and see if that makes sense. So we have the required deflection. Let's double check that. Let's see if they changed this. It was 8 last time. And it's 6.35, so they actually reduced it a bit. So where's del? So this is going to reduce the length required. You're going to see this 63 go down a bit. Yep, 58. And actually, should move that to our inputs. Okay. All right. So we get our required length. We now need to spit out our required. Wait, why is this millimeter times some value? What do we do wrong here? That's always been there. It's saying it's a value to the 2/3. Why? What did we do wrong? Was it doing this yesterday? No, it wasn't doing this yesterday. Yeah, millimeter. So we did something wrong. Hmm. I want to find out why that is. T width. I think it's because we introduced some. Maybe it's because this was a ratio, and I don't actually need to bring this in. No, it wasn't that. Let's print the ratio and see what happens. I mean, actually, we'll print it down here. I mean, pint's a giant pain, but it helps you find your unit issues. So it's unitless. Maybe that's why. I hate when it does that. Okay, that's right. So now, yeah, okay, yep. Having to work with pints while you, I mean, having to work with units while you're actually doing your calculations in real time is kind of a pain, but it is nice because it does keep you honest. Okay, so we have our length, and we should also spit out, our required tab width. I always forget how to do this. I think F strings are so complicated. They really should have, I think there's a better way to do this. Python, if you're listening. If you're a contributor to the Python language. That's some feedback. And then it's gonna be B. How did I break this? Okay, great. So that's our output. So now, if we were to say, all right, let's double the size of the tube. Let's say we made it 100. What happens? The answer is nothing, because it broke. We did this incorrectly. Oh, we need to make this a fixed value there. Okay. How do we do that? I think it is as simple as this. Yeah. So now it'll spit out the new width required for the tab. 6.28. Great. So it is working. So we doubled it and we get doubled the width of the original base. So that's great. We should simplify this though. What was B ratio? Where do we use this again? B ratios times T width. So this isn't actually an input. This goes in the calculations. So we'll add a note here. Okay. All right, now we check for bending stress. Sigma yields. This actually should go to, that should go elsewhere. This goes to inputs. So sigma yield, this will be yield stress of the material. I think it was T5 or T6, I can't remember. Called 7075. And then we also want to put in Young's modulus in here. And I won't get into why temper does not change Young's modulus. It doesn't matter if it's T6, T5, or 5052. Young's modulus is the same for them all. That's just a fact of life. So pull out Young's modulus. And then we actually, let's pull in this, this load. I think we said 10 pounds. Let's recalculate this to make sure it works. It does. Wait, but that doesn't seem right. Lower load. Higher load should be, oh, never mind, it does make sense. So lowering the load means you need less length, which makes sense. Okay, so we want to bring that back to 10 pounds. 10 pounds of press force for the install. So now we're checking for bending stress. C, that makes sense. I, yep, none of that needs to change. Sigma bending. So we're just going through and taking notes and doing the requisite sort of commenting that a good engineer would do. We spit out our values. And so now we get into combining with torsion. And I just want to check all these values, make sure that we're not taking some incorrect values for the inputs. That E should be declared, I think. Actually, can we calculate that as a ratio like we did for base? So right now it's 5. And that's just the distance from here to here. That's tricky. What happens over a length? It is going to change. All right, so let's actually just kind of sketch this out. See what's going to happen here. And again, what we're doing here with E is we're trying to figure out what is the eccentricity of these locking tabs relative to one another. And yeah, we're just trying to figure that out right now. So I'm actually going to copy one of these. Yeah, for the surgery. So we actually only need the geometry over here. We're only going to look at one section of this. And then we only need half of it. Okay. So what determines this eccentricity? So as the material width increases, actually this is here's a fun way we can use scaling. We'll actually just do it by hand real quick. So as we scale this, and what we'll do is we'll scale this by, say we're going to double it in width. We're just going to double it actually and see what happens. So let's think that what should happen when you double the width. Double check that the Z hasn't changed. Nope, Z's the same. So same thickness. When you double the width, do you just double E? Like if this is correct, the distance from here to here, this is originally 3.7, so this should be 2 times 3.7, if that assumption is correct. And it does look to be, yeah, 3.7. So it might just be a rough scale of the width. So the original width times the new width. I think it is that easy. I don't think we have to do anything more complicated than that. Yeah, I don't think we have to do anything more complicated than that, which is great to hear. Um, yeah. So how do we do that? We literally just take a scaling factor on width. We'll do that up here. So we're going to say, hey, what is the, let's find it down here. You tell us your T width is 100. In actuality, it was 50.8. And then we come back down here. We have this E. And so what we're going to do is we're going to say, okay, it's actually a ratio of 50.8. So it's 5. That's what it was before. Actually, let's get the exact value since we're actually really baking this in for good now. It was, let's actually, yeah, let's really find out what that was. Here's the midpoint. Here's the midpoint. So it's this distance, which is parallel 3.7. So this is, and then we had 50.8 for the original. And that's actually the divisor, I think. T width times this divisor. It's going to be our new E. And let's print it out to be sure. See what happens. Oh, we don't have A yet. Why don't we have A yet? Second moment of area. Where are you? J is equal to beta A times B squared by some value. Did we change that earlier? Times A. Where was A declared? I don't think we declared A. So yesterday we actually shipped this with a bug and we don't know what it was. So let's find that bug. What was A? That works. And clearly it's wrong. So let's find out why and how it's wrong. B and H, but we were using, no, this is wrong. So what was this supposed to be? A is the length of the long side. B, did I just leave this out yesterday? Brain's breaking over here. Where's A? Let's find A somewhere. Length of the long side. Okay, I think it really was just A underscore. So 950 millimeters. That's wrong. T width 50.8, T width, oh, it's divided by, not times, because we want that ratio. Yeah, 3.7. All right, we're back in business. That's right. And so now let's see what happens if you double the width of your tube. What happens? Yeah, you double the eccentricity. Okay, this all makes sense now. That's great. Okay. Um, I think I goofed this. I think I left out the divisor. Where was it? No, I didn't goof it. This was right. Yeah. Just to be clear, just to make sure we're right, because I'm trusting this one website. I wanted to give you some citations too, so I'll ask for those citations. So the website left out the half, the divisor by 2. But wait, for plane stress, you get rid of the half. Simplifies to, yeah, okay, so we have it correct. Oh, symmetric. Okay, that makes sense. So, no, I think ChatGPT is wrong here. So it's saying like if this is A, this is B, and this is A, 2, so A squared plus A squared is 2A squared, and it's saying that that goes away. But I don't buy that. Might be going a little bit off track, so I might pull this back and just get back to fixing this and getting into the weld calcs. But I would like an answer on this before I just blindly assume that this is correct. And that is not searchable, so we're not going to use that. So there's the derivation here. Okay. So general plane does cancel out. All right. All right. We'll have this hold for now. Okay. All right. So what do we say we're going to calculate now? Let's get back on track. So we were going to calculate we have L, we have B and H calculated now. H doesn't really change. That's still an input. We want the factor of safety on yield for the weld and the snap. Okay. But first we need input load. And this is not for a snap fit. This is for what we are going to do. Actually, we need to really understand what are the actual loading conditions for this thing going to be. In other words, how much weight can this thing hold, for example? I'm going to get rid of this work we did over here. And I'm going to save my work. Did the naming incorrect on this, so let's fix that. Okay. All right. So what do we have left? So we're going to do input load. Okay, so we have to calculate the input load. So we'll approximate this as, say, a worst case being you take your frame and you eccentrically load it on one side. So let's say you take a load P and you put it at the center. What else would you, how would that actually damage the, is that the worst loading case? Let's ask ourselves that. If you put it here, you're not getting any bending stress because it's resolving directly into uniaxial compression load into this member. So we don't need to think of that. What if we move P over? If you put P here, so P here, no bending. P here, a little bending. And you get bending, bending, bending until you get here. And now that is the maximum bending stress. It has to be, because if you move it back this way, then you're getting closer to the other side. Now we can prove it to ourselves, as we should, by looking at shear moment diagram. So let's do a shear moment diagram real quick. So we have shear. So looking at it this way, we're going to consider this a fixed support. Oh, because it's a fixed, we actually can't. We'd have to draw this as a simple beam, or yeah. Right, we'll just for now look at it this way, but essentially shear is we'll go look at the actual derivations for this to get the real answer, but it's going to look something like this because the edge conditions are symmetric about the center plane. But so we're going to have Vmax here, and that stays like this, and then we get to load P, which pushes it down, and we get negative Vmax here. Now let's look at the moment diagram. So we get moment max, negative, and so that is the integration of the area under the curve here, which gives us essentially an integral of 0 to distance d for a rectangle, which I believe is, or no, is that right? A step function. So this is a constant, I believe. dd. Anyways, I know it looks like this. I do want to go find out how to do this mathematically incorrectly, but essentially you get this. And so the maximum moment is here at the center. Or in other words, it's at L, or it's D, call it length over 2. So it's the distance, so they have functions for each one of these. I just happen to know them off the top of my head, but I really want to remember what the actual mathematical method for this is. So okay, it's the integration of shear. That's right, the integration of shear, the shear value. Because the shear value, get this out of the way. The shear value is constant here. So from 0 to L over 2, it's constant. And so it becomes the integral from 0 to L over 2 of is it a constant? I mean, you can see it's just this diagram here. Yeah, it's VD, yeah, it is a constant x dx. CL dl, which is equal to 1/2 L, right? It's 1/2 LX? No, it's 1/2 CL. I gotta go back and brush up on this. So moment is equal to the integral of V negative, yeah, you get the negative, essentially constant times x. So it's just a line. Let's look up shear moment diagrams. Actually, does the NDS beam EF have this? I think it does. It does. Okay, so we're looking for a fixed beam with a point load. We'll get our shear moment diagram from that. So let's look for that. So this is the one we just did, and that's correct. We're looking for fixed, single fixed, single fixed, single fixed, fixed, and fixed with a load. when it's fixed on the sides, okay, it's fixed on the sides. So interestingly, this was wrong. It's a good thing we looked up the beam diagram, because what happens is this curve actually shifts down and you get the max moment on the end connections as well as at the center. It's saying that here. Your maximum moment is both at the center of the beam and at the end of the beam, which is, I think, yeah, that my intuition kind of follows that, I think. Um, but how does that follow along with this integration here? Yeah, why is this shear moment diagram the same but results in a different moment? Let's go look at the simplified version, or the correctly constrained version. No, that isn't it. So we're looking for a simply supported with a point load in the middle. Yeah, you see what I mean? The shear diagram's the same. Hmm. Anyways, okay, so that's where our maximum moments are. And the value for maximum moment is, that's what we really care about. The maximum moment is this value. So for this case, and by the way, technically the ends here are not fixed because they will pivot a little bit, but we're going to consider them as fixed for now. So you get PL over 8. PL over 8. Yeah. So we can then start to dig deeper into the frame analysis here with this. So what we're saying is, at the ends here, you get a load here. So the actual loading condition at this weld is you get shear, which is equal to P. You get moment, which is equal to PL over 8. And we might actually make this, because I said it's actually a mixed condition of both simply supported and fixed, we might be conservative and say that it's actually PL over 4. So for simply supported beam, in this case, this moment is actually equal to PL over 4. And so we could be conservative and say, well, actually the end condition is fixed, but in reality it's a little, you have room to move it. I mean, it has room to release itself, um, to act as though it's released, because it technically can move in space. So we could be conservative and use PL over 4, because PL over 4 is bigger than PL over 8. And so that's the loading right there. And so is there any additional loading? There could be torque, but we're not going to count that for now. This load wouldn't induce torsion. So it would just be a combination of shear and bending. So we'll do shear and bending checks on the welds. And so now we need to figure out this P. Or how about this? Instead of giving a P, why don't we solve for P? In other words, we'll say, how much load can we actually take here? That would be better. And so let's look at let's look at a weld, because I suspect the welds are going to be easier to analyze than looking at the locking tab. So to calculate a weld, after I ban this person for putting an advertisement in the stream, um, okay. Okay. We're going to calculate the capacity of a weld. So I'm going to freeform say this, having not done this in years, and we'll see how right or wrong I am about it. So when you look at the frame, let's say we're going to look at, actually, you know what's great? We can actually draw the cross section in CAD and then just have it open while we talk about it. So let's look at this cross section here. Actually, it's a little confusing. Let's pull. Actually, let's draw a weld. How about that? So when you weld, you actually get a fillet. And actually, let's talk about what kind of welds you could do. So here you would actually get a fillet weld between this, on this edge, between this face and this face. Same story on this side. The problem is on this side, you don't get a fillet weld. You get a, what do you call this? So you get these welds. You get, so we've already talked about a fillet. I think it's not a lap weld. What is it called? Not a flare bevel. Actually, no, it's not a flare bevel. I think it's a V groove. Yeah, essentially you get a V groove, I think. Well, yeah, it's a V groove. Yeah. So I actually don't remember how to do V groove weld. Fillet weld. It's the most common type you see. This is, you calculate the throat of the weld, and then that is your area you get to kind of analyze against. Um, so yeah. This is the case we're looking at right here. No, actually, we're not. No, 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 this is wrong. Well, it is, actually. It is this. And so let me pull this out. We'll do our drawing over here. So essentially, um, we have our tube. And it's sitting against another tube like this. And we get weld here, and it's a fillet weld. And this is roughly the same as this. And so we need to find the the weld throat size. What is FL and PL? Oh, they're talking about weld patterns over here. I don't know that we want to do that. I actually want to analyze them as individual welds, not as a pattern. So we're not going to do this. It's really annoying that I can't just show you my book that has the answers to this. Is there an open source book that I can just pull from? Nope. How about this? Machine design PDF. Look for weld. Nope, not working. Okay, that's not working. All right, simple bullet weld analysis. I do not want to derive this. Like, deriving this is going to be a giant pain. Okay, here we go. This is what I was looking for. So essentially, when you analyze a weld, you're looking at there's a couple things. So you look at how the weld fails, and that's the way you get your area. And so you are looking for the weld throat, and that's usually 0.7, I believe. Uh, it's the book I use for this. So I'm sorry, I have to use the book and I can't show it to you. I'll just write it out. How about that? Bear with me for a second. Welds, welds. Okay. So the way this works is you have a weld under direct load. You have H, and you also have H on the other side. And this is essentially your length. Sorry, dog. And then you have the length of the weld into and out of the page. And the throat here is the throat, and that's call that T for now, but T is equal to point 0.0, I'm sorry, 0.707 times the length, or H. And that's the value you get to use for making this analysis. And so for shear stress, so you actually have, remember, stress is, well, in a case for welds, it's similar to F over A, but in this case, it's really, make this look not terrible. For welds, it's roughly like that, except it's F over, and then your A factors in this fact that your weld throat is different from your length of the weld, or H, and so it becomes H times L, where L is the length of the weld. Okay, so now we can figure out what the strength of our weld is. We're getting there. So we're going to check against shear stress, and that kind of makes sense, right? Because when I pull on this tube, it's going to act and shear in that filler weld. And we're only going to do 2 welds for now. And it's going to be over this length. And that length is just the width. So we'll actually start drawing this out. I mean, not drawing, we'll actually start calculating this out. How do you do roughly equal to? Prox. Nice. Okay. So now we can get to calculating. So the width of the fillet weld. So generally for 1.651 thickness tube, that's 25.4, that's 0.65 tube. Roughly, that's going to be a pretty small weld. Like you can't get a 1/4 inch weld on that. 1.5 times the thickness. So that's So it's 0.065. So that's a 3/16 inch weld. So H is equal to 3/16 inch. What is L? L is going to be the width of the tube. And then the number of welds. We're only doing 2 of these. So what's our pull load here? Actually, we should regress what the actual loading turns into. So this is actually going to be normal stress. This isn't, well, all right, we're going to do some gut checks before we start getting too deep into this. So this is, the pull force is going to be, oh man. So we have a moment, right? We need to resolve this. So what I'm saying is, for this case that we're approximating here, we're saying P acts down here, and then this weld here is going to have a load that does this and this. And the way you find that is you call that F1. It's actually reaction 1. And this is reaction 2. Reaction 1 or 2 are going to be equal, but to figure that out, you need to do you need to resolve the moment of this cantilever. And to do that, you're going to say, okay, look, the moment's going to be roughly equal to so the moment is equal to, we said PL over 4, which is also equal to the reaction moment, or to the reaction forces, which is L over the distance between the load here. All right, I'll draw the free body diagram. I didn't want to, but so we're approximating this as a simply supported beam. We have P here. We're analyzing the weld right here. You get some moment, the sum of the moments about A, it's point A, is equal to E, this distance. It's about E. E times P, the load. Oh no, we already did that. Sorry, this is wrong. What we're looking at is, yeah, ignore all this. This is wrong. What we're doing is we're saying this tube is going to have a reaction force this way and a reaction force this way. And that's going to take place at a centroid here, which is the length of the tube, or actually the width of the tube over 2, right? And so this is going to equal width over 2 times R. And there's 2 R's, so you multiply that by 2, right? Yeah. And so now we have PL over 4 is equal to essentially 2's cancel out, right? Yeah, it's equal to WR or RW, which is the R is the reaction force, W is the width of the tube. And so now we can go solve this. So if we write this all out in LaTeX. Let's keep doing that. Moment. P over 4 is equal to not omega. Width over 2 times R times 2, which is equal to PL over 4 times, okay. Then we solve for R. Yeah, we'll actually just, yeah, okay. So this then turns into this. R is equal to, R1 and 2 that is equal to PL over 4 times width, or the distance between, well, width of the tube. Okay, and this kind of makes sense. So the wider your tube, the less force required because this number goes down. The longer the length, the more reaction force you need. That all kind of checks out. So we'll write this out real quick. We get fraction, what do we say it was? PL over 4W. Okay. Okay. Okay, so let's see. PL over 4. So I think we have all the variables we need here. So we'll have r sub 1, 2, which is actually, we'll just call it, so r sub welds is equal to p. Oh, we haven't determined our p yet. Actually, we solve for p, don't we? Because we're trying to find p. Yeah, we want p. Solving for p. So this is p all over 4w. We get 4w. So we get r times 4r w, and then this is divided by L, right? So these move up, this moves down. P is equal to R, no, 4RW over L. Okay. We don't know what the reactions are yet. Do we need to know them? We substitute this into the stress equations, I think. Actually, I think we're going to need both of these. Dang, I lost it. I think we want to put this in terms of how do we get this in terms of, I think we solve for R like we did before. I think we solve for R. We solve for, we need the, all right, we need the force on the tube, pulling the welds out. You get that through the reaction forces that counter that load, which is result of the moment, which is this, which is eventually this. Problem is we don't know what R is. All right, we'll keep going. I'm gonna go back to solving this as an equation that just solves for the reaction forces because that's what's going to go into the weld, and I'll think through this more later. Um, that was PL and then over 4W. Okay. All right. We don't know P yet, right? All right. Um, I'm burning out on this, so I'll leave this for tomorrow, and we'll get to actually calculating what this has to be. What I'll do in the meantime is commit this. So if you have a thought on this, please let me know. Um, and I'll also push the cat out. So I'll do that right now. So this will go under unreleased. Save this. All right, you can find this on the repo now. Okay, I will see you tomorrow.